So on number 61, ladies and gentlemen, excuse me. Number 61, you'll notice that it says chunk cube, which means how many times you multiply the chunks together? 3 times. So the easiest way I can think of telling you guys how to do anything is jump the cube, jump to the fourth, whatever. Just write it out 3 times. Go 3 times and you get 2x plus 3y. 2x plus 3y. 2x plus 3y. You cannot distribute that exponent into the parentheses because of the addition symbol. Okay? I can't distribute that in because of the addition symbol. If the addition symbol wasn't there, if it was just 2x, 3y all multiplied together, you could have done that. Then that would have worked. But since there's an addition symbol there, that means it's a binomial. You have to multiply it out. Okay? So now, when we did this one like this yesterday, I said take care of the second and the third ones first, and then distribute going from left to right. It makes it cleaner. Foil this out, you're going to get 4x squared. 6xy plus 6xy is 12xy plus 9y squared. Very good. Now you have that double distributed property. Distribute the 2x to all 3 parts, and then distribute the 3y to all 3 parts. So you get 8x cubed, 24x squared y, 18xy squared. When you do these types of problems, when you have x's and y's, put them alphabetical, and just keep that consistent. That way, when you go to combine your like terms, you don't try to forget which was which and all that stuff. Do it again. The other 3. 12x squared y, 36xy squared, and with 27y cubed. Okay. 3 distributed from the first part, 3 distributed from the second part. Now I got a whole bunch to try and combine. This goes back to your combined like terms now. Start with your 8x cubed. Underline your x squareds. 24 and 12 is 36x squared y. Go to your y squareds. 54. And you're left with 27. Yeah, that's fine. That's not a big deal. I usually just leave it in that method as you're going through there, because later on there's something that we do in chapter that's called binomial expansion, where you learn about how you use Pascal. You guys did Pascal's triangle with Seth a little bit? So Pascal's triangle, where how things multiply through. Pascal's triangle allows you to figure out coefficients of binomials as you expand them out. So eventually in second semester, when we talk about that, I'll ask you what is the coefficient of the variable that has the x to the 8th term in this following binomial that has like a jump to the 50th. And there's a method to doing that with combinations and stuff. Pretty easy, but we'll do that later. Any others on 63? I know that one's been asked a lot, and it usually is because everybody just wants to write it as 8x cubed plus 27y cubed. You can't do that. It's puppies. It's puppies. Sarah McLaughlin will just follow you around and just keep singing in the eyes. Angel, yes, thank you. Yes, the ASPCA commercials that just, you have to change the channel as fast as humanly possible before you want to. That's a great persuasive speech. It makes me feel bad, and I just have to change the channel as fast as possible. It's like on the radio, you hear 1877 cars for kids. You're like, it's making it go away. Make sure your names are on that. Send that up. Let's talk about binomial or. So yesterday you missed it on this one. Guys, Miss Yule wasn't here yesterday to hear the quote that was pretty funny, but it was, holy shit, look at the astronomical function. Wow. I thought it was funny. I know Christine, she thought it was the greatest thing since sliced bread, right? So, no, I don't know what Amy's laughing at now. You okay? Yeah. Please. Why are you crying? I don't think she's laughing at the joke. I'm going to go on a limb with that. Wait, what is the thing from in a suitcase? What is it? In a phone booth of emotion? What was that from? Anchorman? Was that right? No, not Anchorman. Different movies. It is a bad look. I'm just going to go ahead and tell you that. If you pull it too hard, it's going to really hurt your brain, I think. Anyway, factoring polynomials and stuff like that. This is very similar in the fact of how you guys have done some of your polynomial stuff before. But the polynomials that you guys have worked with started out as trinomials. Trinomials and binomials are polynomials. They have to have two monomials or three monomials. Now, as we go on, we start talking about nth degree polynomials and factoring of them. We'll have more and more terms. So what I want to do is just start with something very simple and think about the idea of factoring. If I wanted to factor 4x squared and 4x, what is always the first rule of factoring? It's find the GCF. So if I do and go back and find the GCF, what's the GCF of 4x squared and 24x? 4x, good. So if I factor out of 4x, I'm left with x minus 6. Is that fully factored form? Okay. What are your tails doing? Up. Okay. Positive, even exponent. They're up. Now, what would change in this problem if I said what would you do next, though? Solve thing. When you have something equal to 0, there's a difference. There was a difference when we did this before as well, when we did factoring quadratics. If it said factor, you wrote factors. If it said solve, or it said equal 0, you had to find their zeros. So if this happened to be a problem where it was equal 0 at the very beginning, you cannot add 24x divided by 4. That does not work. Okay? That eliminates possible zeros. Here, that means you have two terms that you set equal to 0 to find your zeros. That was what we've done in the past. Just a reminder of the difference in the vocabulary between solve versus factor. Okay? Excuse me. Same thing goes for the 2x squared, 11x, and a minus 21. We've done this one before as well. Obviously, again, you always, first rule of factoring is to see if you have a GCF. 2x squared plus 11x minus 21. Pretty sure they don't have anything in common. Actually, they do have something in common. What do they have in common? 1. Good. Very good. But does that help us with anything? Not at all. So now, when we factored this problem before, we multiplied our tails. What's 2 times negative 21? Okay. What times what multiplies to negative 42 that adds to positive 11? Well, go through your factors. If you have to start at the beginning, start at the beginning. 1 and 42. 2 and 21. How do you know if 3 goes into something? Do you guys remember the trick? Very good, very good, very good. I don't know if you remember this, but if you add the decimals, or add the digits together, 4 plus 2, and if that's divisible by 3, it's divisible by 3. So 3 times what is 42? Which one of those combinations, I'm going to stop there, will get me to 11? Negative 3 and the positive 14. Okay? It's so nice, it's like a slice of pie. Okay. Do I have to put the negative 3 before the 14x? I can flip-flop them. It's preferred to put the negative value first because it's less of a headache as far as your factoring via. So what happens here, if you start with 3 terms, we split that middle term into 4, then you can factor because of what's called grouping. What we're looking for here are GCFs. 2x squared and 3x, what do they have in common? X. If you put 14 in front, then yes, you're on that right track. So you have 2x minus 3. 14 and a 21, what do they have in common? 7. Is it a positive or a negative 7? It's a positive 7 because our term here was positive. And I'm left with 2x plus 3. Are the two things in parentheses the same thing? Yes. That's a really good sign. Okay? So you write it down. And what's left? And your factor. Okay. What direction would this go? Tails. Up again. Very good. It goes up. What are yours? If this said equal 0, what would your zeros be at? Ooh, careful. Positive 3/2 and negative 7. So, what do we do now when we have this? Usually what happens, you don't go further with more groups, usually what happens if you're factoring because of grouping like that, if they don't match, it just means you made a mistake somewhere. It means your terms weren't set up correctly. So you have to start over. Or you factored out the wrong GCF. That's usually what happens. Okay. So here, you got x cubed plus 27. Now, we haven't seen one like this before. But we've done one like this. What was that called? Not a perfect square, a difference of squares. Remember, difference of squares, we would ask the question, is the first term a perfect square? Is the last term a perfect square? Is that a subtraction symbol? Did you say yes to all 3 questions? Yes. So then your terms would have been that. Okay. Now, what's different then is now what? It's not even squared, it's cubed. So now we have to talk about what are called sums and differences of cubes. Let me take this to a different sheet. We'll have there's a formula for factoring what's called a sum of cubes, and there'll be a difference of cubes as well. All right. Now, the way that textbooks and the way that I'll represent this is basic. You start with something cubed plus something else cubed. They use A's and B's a lot of times. Now, in order to factor this using this special pattern, it always starts with the A plus B. It's going to be A squared minus AB plus B squared. And then the other one is the difference, so difference of squares. I'm sorry, difference of cube. Look at how the signs pattern themselves out. If you have a sum, it goes plus, minus, plus. If you have a difference, it's minus, plus, plus. The first part is always the same sign. The next sign is always opposite. The last sign is always positive. Okay? Same, change, same. Same, change, positive. Same, change, positive. So if it's a sum, same, change, positive. So it's the same sign, change the sign, positive. Plus, minus, plus. If it's a difference, same sign, change it, plus, minus, plus. So when you go back to the idea of where we had x cubed in a 27, that means you'll have to be able to figure out cube roots. But more often than not, your cube roots, they don't tend to go any larger than like 6. Every once in a while, you might see a 7 cube. But you have a calculator, it's not that bad. So what is the cube root of 27? 3. So that means that this is the exact same thing as saying x cubed plus 3 cubed. Do you agree? So that means your a value is playing the role of x, and the b value is playing the role of 3. So to factor that, you're going to get x plus 3, x squared minus 3x plus 9. Okay. So back to where I was here.
All of a sudden, we'll all start talking like this because they just pump the whole system full of helium.
All right, first rule of factoring is what? UCF, okay. Now, in this case, everybody agree everybody agree that there's an x squared that they both have in common? Now, if I take the x squared out, I'm going to have an x cubed, which means I have to figure out how do I find a perfect cube out of the 16? What's a perfect cube that's hiding in the 16? Well, 2, if I cube 2, what do you get? 8. So if I factor out a 2, if I take out a 2x squared, I'm left with 8x to the third, and what's half of 250? Is 8x cubed a perfect cube? Is 125 a perfect cube? Yep. So this is the idea then. You have the same thing as saying that. Now, when you have that coefficient out front, you gotta be careful in how you go the rest of the path. So the a value and your a cubed plus b cubed part, or a cubed minus b cubed, this is different. A value is playing the role of 2x. So the pattern then is going to be a minus b, a squared plus ab plus b squared. Your value of a is 2x. Okay? So bring down your 2x squared. You're left with 2x minus 5. What is the quantity 2x squared equal to? What is the quantity 2x squared? Thank you. Morris. Multiply those two values together, you're going to get 10x. Square the last term. 45. That is fully factored form. That is your fully factored form. Yes, ma'am. No. And that's a good question. When you get to that last part, when you do your difference or your sum of cubes, the last trinomial is not going to be factorable. Okay? If you had to find its zeros, you'd have to use the quadratic formula. What's that? No. This was just a GCF. This was just starting this into GCF and bumping up. The a value was the cube root of x, the 8x. That's right. Or the b value that was 5. Okay. We got both. Sorry to bore you. A times b. What's a is 2x, b is 5. Nope, remember the signs. Same, change, possible. I'm looking at literally the a value is 2x, the b value is 5. Sign patterns, just follow the sign pattern. Okay, don't worry about it being positive or negative. All right. Which then gets us to be able to do stuff, like this. We talked a little bit about this problem yesterday. What is the degree of this polynomial? It's a third degree polynomial, which means it should have up to how many terms? 4 terms. What are the tails doing? They're going. They're down, up. They're going. Yes, they're going. What direction are they going? They're going down, up. Okay. It's good radio, that song. But anyway, how many possible zeros could we have? 3 possible zeros. And how many possible changes of directions can you have? 2. Remember, change of directions is 1 less than your degree. Terms is 1 more than degree. Right? Now, whenever you have, bless you, whenever you have 4 terms, it doesn't matter what the degree is. you're always going to want to try to factor because of a factor via group. Always group them first. Always factor by grouping. What's that? Sorry. Okay. Always factor via grouping to start. Whenever you have 4 terms, doesn't matter what the degree of the polynomial is. Always factor via grouping. And then go via GCFs. In that first term, you have an x cubed minus 2x squared. What do they have in common? Factor it out. The next term, notice I did that add the opposite before I grouped the parentheses. The reason I did that is to remind myself to factor out the negative. What does a 9 and an 18 have in common? The 9, but I'm going to take out the negative 9. Are those two things in the parentheses the same thing? Again, that's a really, really good sign. So you write that down. What are you left with? X squared minus 9. Now, what happens with this upper degree polynomial mumbo jumbo is that from time to time you have to look at where you're at and say, can I go further? Can I go further? Yes. Why? What is that called again? Difference of squares. Good. So you're left with x minus 2, x plus 3, and x minus 2. Now you're fully factored. Okay? You're fully factored. All right? This is why algebra. This is where we're getting to. Why does everything work? Well, can you do, what's your tail dance? It's odd exponent, positive value, so you're down up. Where are your zeros? So your tails are down, up. Your zeros are at -3, +2, and +3. So that means it has to go up, change direction, and go up. That's all that means. So don't say you hate graph. If you know your tail dance and you combine zeros, you can do this. That's the whole idea. Can you get to that? We're getting to that. Don't worry about it. We're not there yet, but we're getting there. Okay? All right. What changes here? We're going to set it equal to 0. When it's equal to 0, what do you have to find? The zeros. Okay? So when you have that, that means you have to find, guys, you got to find the actual zeros whenever you see an equal sign. So you have to set one side equal to 0. So what I would do is if I were you while you wrote this down, I would write it down just like I would normally, 3x cubed 7x squared minus 12x minus 28 equals 0. I would write that down as I go through the problem. And then I factor by grouping. And the reason why I want to factor because it could be a grouping is because how many terms are in this sequence? So 3x cubed and a 7x squared, what do they have in common? Squared, good. I have a negative that went into that third part there, so we're taking the negative out. What does a 12 and a 28 have in common? Think bigger. 4. Because I want it to look like that first thing in parentheses. Okay? So if I take out the -4, and I have 3x plus 7. So if you took out just the 2, you would have had 6x plus 14. And then, oops, they don't look the same, which meant I had to go back and see what I screwed up. Okay. Are those things the same in the parentheses? Write it down. Which means your final 3 terms then would be 3x plus 7. And where are your zeros located? 2, -2, and -7/3. Okay? That's the idea. Right, that's the idea. Now, what's going to change when you have higher degree polynomials? It's a little bit more math, but it's not the complexity of how you set up and go for it doesn't change. There are certain tricks that you're always going to kind of follow through with. No, I want to do this one. It's a higher degree polynomial. I have 81x to the 4th minus 16. Now, one of the things you would look at first of all is obviously see if there's a GCF. No está aquí. There's no GCF, okay? But notice how many terms are there? 2. What's the sign in between them? Minus. So that should be going off that maybe this could be a difference of squares. What's the square root of 81x to the 4th? 9x squared. What's the square root of 16? Is that subtraction sign? Yeah. So that means you get 9x squared minus 4, 9x squared plus 4. Can I go further? Yes. What's that? All right. What's the square root of 9x squared? What's the square root of 4? Is that a subtraction symbol? Yes. So therefore, the first term can get broken down into 3x minus 2, 3x plus 2. All right, let's try the second one. Is 9x squared a perfect square? Is 4 a perfect square? Is that a subtraction symbol? No. You're done. You said no, so you stop. That is fully factored form. That is fully factored form. Because in this case, you have what degree is the polynomial? 4th degree polynomial. What are the tails doing? They're up, up. Tails are up, up. Now, that means how many possible zeros can we have? 4. We can have up to and including 4 possible zeros. Well, in this case, we have 2 real and 2 imaginary. Okay? If, we're not there yet, but if that equals 0, that means you'd have to set everything equal to 0 and solve for x. Well, 2/3, negative 2/3. Here I'd get 9x squared plus 4 equals 0. Well, you know how to solve that equation. You've done that. Subtract 4 divided by 9, take the square root. You get plus or minus so sorry to get ahead of myself. 2/3 I. So it's still, even though it's a 4th degree polynomial, well, you're going to be doing a lot of it. So means you're going to have 4 possible zeros because algebra is going to algebra. We're getting there. Okay. All right, let's do this one. (4x to the 6th minus 20x to the 4th plus 24x squared. Think bigger. There you go, you're getting there. So in this case, it's got 3 terms. Notice how your exponents, I'm sorry. First things first, always go for the GCF. You guys all said that your GCF was 4x squared. So that leaves you what on the inside? Okay? Notice how your exponents are getting cut in half each time. 4, 2, 1. See that? So that means I can ask the question, what times what is 6 to add together to get negative 5? Or negative 3 and negative 2? You want positive 6, negative 5. Means they both have to be negative to multiply to add to the negative. Okay? Now watch what happens with your exponents. When your exponents are being cut in half in a trinomial, 4, 2 to an exponent of 1, you can write it like that in terms of their terms, because if you FOIL that out, you get x squared times x squared, which is x to the 4th. Negative 3x squared minus 2x squared is negative 5x squared. Negative 3 times negative 2 is positive 6. So you can factor trinomials that have their exponents being cut in half as you would any other trinomial. You can factor it exactly the same way. Okay. Now, here's where it gets interesting. This is where I want to make sure you guys understand a couple of terms that are going to come up, like vocabulary terms. What was the degree of this polynomial? There's a 6th degree polynomial. What was the first term, positive or negative? So what are your tails doing? They're up, up. Okay? Which means how many possible zeros can you have? 6. So always, zeros are always the same. You can have up to including the number, whatever your nth degree is, that's how many possible zeros you can have. All right? Now, if I'm going to try to find my zeros, that means I have to set each individual term equal to 0. You guys okay with that? Yeah. All right. So that means that we'd have x squared minus 2 equals 0, x squared minus 3 equals 0, and 4x squared equals 0. What does x squared represent? 2x's, all right, as in like x plus x, x times x. Okay, so would this be the same thing as saying 4x equals 0 and x equals 0? If I split this apart to saying 4x times x? Means the same thing, doesn't it? You can write it as 2x times 2x. It doesn't matter, because and when you take out the GCF like that, when it's a monomial, the scalar out front doesn't make a difference. Okay? So that means I have a 0 at 0. I have a 0 at 0. These zeros are at plus or minus the square root of 3. And these zeros are at plus or minus the square root of 2. What was the degree of this polynomial again? Do I have 6 zeros there?
Yes.
Yes. One of them was repeated. Which one of those was repeated? 0. So anytime, and I hate the fact that this is a 0 that's being repeated here, but anytime you have what's called a repeated, any repeated 0 is called having multiplicity. Multiplicity. That means the 0 occurs at the same value more than once. It just so happens that the multiplicity here occurs at the value at 0. If it was 2 zeros happen to be at 8, 8 would have multiplicity of 2. 0 here has the multiplicity of 2. If there were 3 8s, that means the 8 would have multiplicity of 3. If there were 3 zeros, 0 would have multiplicity of 3. There's a little trick that happens. You've done this before. When you factored x squared plus 6x plus 9, that meant your zeros were, your terms were at x plus 3, x plus 3. Where were your zeros located at? Which meant that when you graphed it, it touched the x-axis at one spot, didn't it? Which meant that since this is an up, up, it changed direction. You've done this before where you've had multiplicity just didn't know what it was called. This term comes up a lot from here on out. So I wanted to say what it meant today, because now when we go to looking at this 6th degree polynomial, tails are going up, up. Get the scratchy face, it's all right. We're just building up to it. We got a long ways to go. All right, we've got tails that are up, up. I have zeros at negative root 3, negative root 2, 0, root 2, and root 3. Even though there's only 5 spots that are zeros are occurring on this, I know my tails are going to be up, up. And as it goes through, change direction, change direction. It'll do that. When you have even multiplicity, it changes direction at that value. If you have odd multiplicity, it goes through that value. It'll come back up later, but just so you know right now. This case, if you graph this, it's going to look like a funky W, like double W's. Yes, Andrew? It changes direction after that. It goes through. It just goes through it, yeah. And we'll come back to that later on, Dennis. I don't want you to worry about that right now. When we get into 6.6 or 6.7, when this shows back up again. But as we go through with a lot of this stuff, especially with polynomials, since it builds upon the vocabulary throughout this entire unit, the sooner I start talking about tail dancing, what zeros represent, changing of directions, as we go to build these things out later on, it's going to be a lot easier because you won't be blindsided with it. You'll understand when I'm talking about zeros, real zeros, non-real zeros, things like that. Okay, this is where we're heading. We're getting there. Tonight, all I wanted you guys to do, it's on, what is this, 6-4? Yeah. I forgot the page number, but I already put it on the calendar. I want to say it was numbers 33 through 66 every third. Okay? It's every 3. So we'll go through those. There is nothing about finding zeros on tonight. We'll do more zero stuff tomorrow, as well as how do you build these things and find value out of a word problem tomorrow. The word problems with polynomial stuff is very similar. I should say it's a little bit easier than trying to deal with the quadratic stuff because there's really only one way to do that style of word problem. So we'll go from there. But like I said, I remember the page number, but just go through the PDF file and figure it out. I think it happened in one of the other classes. Oh. Did it sting like a bee? Float like a butterfly?